This is where it ends. A single chip, uniformly shaped, evenly seasoned, precisely fried. The result of a process that spans fields and laboratories, milling machines, and robotic instrument judgment. From above, the scale of the operation becomes clear. Production buildings, warehouses, loading bays, and the infrastructure that connects them all. This is the physical reality of modern food manufacturing. And so the product leaves the facility. It has been made from raw agricultural material, transformed through a series of precisely controlled industrial processes, inspected at every stage. When a deviation is detected, the affected product is immediately quarantined. It is placed in a designated and readable from the product flow. It will not move until the investigation is complete, the root cause is identified, and a disposition decision has been made and documented. The production monitoring room is the nerve center of the facility. Every sensor, every instrument, every automated system feeds the status of every line, every parameter, and every ongoing process in real time. Decisions are made here based on data, not intuition. All quality data collected across the shift is fed into a central quality management system. Trend charts show how each parameter has behaved over time. The system monitors for drift. Texture is measured with equal rigor. A penetrometer presses a probe into the chip's surface under a controlled load rate and records the force at which the chip fractures. This value, false color measurement, is carried out using spectrophotometric instruments that quantify the exact shade of each chip sample at a column-stand. The instrument provides the objective numerical record. Quality control does not end when the product leaves the production line. In the facility's laboratory, samples collected throughout the shift are tested against a full panel of quality and texture, are all measured systematically and recorded. Water is similarly managed with care. Treatment and recycling systems reduce the total water consumption of the facility by cleaning and recirculating water while used in washing through approved treatment paths. Every liter is accounted for. Modern food manufacturing facilities are also actively managed for energy efficiency. Heat recovery systems capture waste heat from the fryer of the facility or forms part of its broader environmental management program. At the end of every production run, the cleaning begins. Cleaning-in-place systems pump food-grade cleaning agents through the internal pipework and process equipment, sanitizing surfaces that cannot be accessed physically without disassembly. Dedicated work clothing is worn by all personnel in the production environment. Hairnets, gloves, and facility-specific footwear, watches, and mobile exist because can never need inside production area. Every entry point to the production area is a hygiene checkpoint. Hand-washing protocols are mandatory for all personnel before they enter and after any break. The stations are automated, ensuring the physical environment of a modern food manufacturing facility is itself a quality control tool. Every surface in the production area is smooth, non-porous, and designed to be cleaned completely cumulate. When an order is dispatched, pallets are picked from the warehouse and loaded onto delivery vehicles. From this point, the product enters the distribution network, moving to regional warehouses, then to retail distributions. The finished goods warehouse is where the product waits before it enters the distribution network. Every pallet is logged into the warehouse management system on arrival. Its location is tracked, its age is monitored. A final pallet label is applied, completing the traceability chain. This label identifies the product, records the production date and batch codes present on the pallet, and provides the information needed for the warehouse management system to track its location from this moment until the moment it leaves the facility. The completed pallet passes through an automated stretch wrapping station. The machine spirals film around the empty base top. The wrap secures the case against shifting during transport and provides a degree of protection against moisture and contamination. Layer by layer, the pallet builds. Each case is placed with the same accuracy as the one before it. The robot does not tire, does not vary its errors. The completed pallet is structurally sound, dimensionally consistent, and ready for wrapping. In the palletizing area, robotic systems take over. Sealed cases are picked up one at a time and placed onto pallets, and procedure is not arbitrary. It is necessary to delivery vehicles and warehouse racking. An outer label is applied to each sealed case, carrying its own barcode and batch code. This outer code links the case to the units inside it and to the raw materials and proprietary tube it contains. The tape is applied across the top and is synced through the sealing station. As the case emerges, sealation is scored, ready and ready for the outer label. The process takes less than a second per case. An automated pick-and-place system loads the labeled tubes into each case in precise rows. The robotic arm moves with programmed accuracy, placing each tube in its identical to every other case coming off this line. In the secondary packaging area, automated case erecting machines take flat cardboard blanks and form them into open boxes in a continuous, rapid cycle. Each case will hold a specific number of tubes in a defined arrangement. Inline coding equipment applies the best before date and a unique production code to every single unit. This is not merely a date, it equates this specific selection in the. Each sealed tube now moves through the labeling station. Labels carry all legally required information: ingredients, nutritional values, allergen declarations, meat and country of origin. The plastic resealable lid is applied to the top. It snaps into position under controlled pressure, seated firmly enough to seal, but designed to be removed and replaced by the consumer without requiring excessive force. With lid on and base sealed, the tube is complete and the product is protected. The metal base is crimped onto the bottom of each tube by a mechanical sealing head. The action is fast, precise, and continuous. Once sealed, the base provides structural rigidity to the tube and an airtight closure at the bottom. The product is now enclosed on one end. Every filled tube passes over a precision check weigher before it proceeds. The fill weight must fall within a tight tolerance, a deviation of just a few grams in either direction accurately to what is inside the container. Looking down into the tube as it fills, the engineering logic of the saddle shape becomes completely clear. Each chip nests into the one below it with almost no gap. The stack is stable, dense, and perfectly ordered. The filling process depends entirely on the uniformity of the chips. A stacking mechanism orients each chip and loads it vertically into the tube, one overlapping the next in a continuous column. The packaging station is where the product takes its final, recognizable form. Empty tubes arrive upright, in a continuous single-file stream. Every chip also passes through a metal detection system before it reaches the packaging area. The production environment is designed to prevent contamination. Any product that checks and functions as alerted and quarantined for investigation. No exceptions. When a chip is identified as falling outside the acceptable range, too dark, too pale, misshapen, or cracked, a precision air ejector is spun instantly. A target is across the line and line palm floods. The inspection speed is remarkable. Each chip passes through the camera field in a fraction of a second, and within that time it has been photographed, analyzed, and either cleared or flagged. The system processes thousands of chips every minute without slowing the production line. As the chips cool, they pass through automated vision inspection systems. High-speed cameras mounted above the conveyor photograph as each chip process each space lock in real time. The cooling must be managed carefully. Too rapid, and the chips become brittle and prone to fracture. Too slow, it doesn't enough heat to cause problem to the airflow and the ambient conditions of the cooling zone. You never all calibrate. Before the chips can be packaged, they must be cooled. Sealing warm chips inside a container would generate condensation, and condensation is the fastest route to a soft, degraded product. At regular intervals, trained quality assessors collect samples directly from the line. They assess the chips physically, examining coating evenness. This is one stage in the process that no analytical instrument has fully replaced. The result is visible in every chip that exits the drum. Each curved surface, concave and convex, carries an even, consistent layer of seasoning. No pooling in the hollows, no bare edges at the rim. The seasoning is not applied freely. It is dispensed by a precision dosing system that monitors both the flow rate of chips on the line and the rate at which seasoning is being released. The two are held in a specific, calculated rate. Inside the drum, gravity and rotation do the work. Chips tumble end over end while seasoning powder falls through the air around them. Each refers a new surface to the falling seasoning. The goal is complete, even coverage. No bare patches, no excessive buildup. The balance is precise. While the chips are still warm from the fryer, they enter the seasoning system. Warmth and residual surface oil are both essential at this stage. They act as the adhesion medium for the seasoning powder. In slow motion, the quality of the fry is apparent in every chip. Uniform color, consistent curve, a surface that catches the light evenly across its entire area. As the chips exit the fryer, they are fully cooked, golden brown, and structurally set. Their saddle shape is now permanent, locked in by the heat. Excess surface oil is your way toward the next stage. They are hot, fragile, and not yet ready for packaging. Oil temperature is monitored and controlled at multiple points along the fryer. Even small deviations from the target range, for the seasoning rate, will hold system to temperature within its specified window continuously. The oil does not sit static in the fryer. It circulates continuously through filtration systems that remove fine food particles generated during cooking. A controlled proportion of the oil is replaced with fresh oil on an ongoing basis. Under slow motion and high magnification, the frying process becomes visible in extraordinary detail. Each bubble rising the chips is charged as a microcep's pocket added, leaving the dough in as steam. The moment the raw chip contacts the hot oil, the transformation begins. Moisture inside the dough converts to steam almost instantaneously, and that steam is the gives of the chip light, porous texture we associate with a perfectly fried crisp. The shaped pieces now enter the most technically demanding stage of the entire process, the fryer. This is not a conventional frying setup. It is a large, continuous flow industrial cooking system. The shape has a formal name in mathematics, a hyperbolic paraboloid. It curves downward in one direction and upward in the other, simultaneously. This geometry allows each chip to nest perfectly inside the one above it. From above, the forming conveyor is a study in geometric repetition. Each piece holds its curve. It is the engineering prerequisite for everything that comes after, including the packaging system itself. In slow motion, the transformation is elegant. The flat dough piece settles onto the curved mold, its edges drooping gently as gravity and the pliability of the dough do their work. The double curve, the forming section, is where the chip's identity is established. Each flat oval piece is transferred onto a curved saddle-shaped mold on the conveyor. As the piece moves forward, it conforms to the shape beneath it. What enters as a flat oval will leave as something architecturally precise. The cut pieces move forward in orderly rows. Each one is perfectly oval, perfectly flat, and perfectly uniform. But they are missing something. The shape that defines this product, that distinctive double curve, has not yet been applied. That comes next. The dough that remains between the cut pieces, the lattice of scrap, is not discarded. It is immediately collected and fed back into the production process. In a well-run facility, material loss at this stage is minimized to near zero. Under slow motion, each cut is clean and decisive. The raised edges of the die compress through the dough sheet and release a perfectly formed oval piece with each revolution of the drum. Thousands of these cuts happen every hour, each one identical to the last. The cutting station uses a rotary die, a large drum fitted with raised cutting edges in the exact outline of the finished chip. As the drum rotates against the moving dough sheet below, it steps from above. The sheet is flawless. Edge to edge, end to end, it is perfectly uniform. This consistency is not easy to achieve at industrial scale, and it does not happen by accident. In slow motion, the compression is remarkable. The dough enters the nib point to soft, thick mass between the merge sheet, frick mass, and emerges as a smooth, even sheet. With the dough prepared to specification, it moves into the sheeting line. A sheet sits of stainless steel line to percent in thickness. Each pair of rollers is set fractionally closer together than the last. Inline sensors monitor the dough continuously as it mixes. Viscosity probes measure consistency in real time, feeding data back to the automated control system. If the dough trends outside its target range, the system manages. As the mixing paddle turns, the paste and dry ingredients gradually come together into something new. The dough thickens, becomes cohesive, and begins to hold it. It should be pliable without being sticky, firm without being crumbly. The paddle does not stop until those conditions are met. Every ingredient is dispensed by automated dosing systems, not by hand. Hoppers and silos feed precise quantities of dry material into the mix according to a formula that has been tested, validated. Into the mixing vessel, the fresh potato paste is combined with dehydrated potato flakes. The flakes absorb excess moisture, bringing the water content of the mixture down to a precise, workable level. The paste that emerges from the mill is dense, smooth, and uniform. Under slow motion, its consistency is almost architectural, a continuous controlled flow of raw potato reduced to its most workable form. This is not cooking, this is engineering. Rather than being sliced into rounds and fried directly, as conventional potato chips are made, these potatoes are ground. In this place, this terdim hill de protein, potato dough. The peeled potatoes emerge pale, smooth, and slightly damp. They look unremarkable at this stage, but they are now clean, prepared, and ready to enter a process that has no equivalent in conventional potato chip manufacturing. The removed skills, water, and starchy residue are not discarded carelessly. They are collected and diverted to a dedicated waste processing stream. In a modern facility, this material goes on to be serviced. Inside the drum, the abrasive surfaces do their work continuously. Potato skins peel away in thin strips as the tubers tumble and rotate. The machine is calibrated carefully. Every gram of raw material has value. With washing complete, the potatoes move directly into the peeling stage. Industrial abrasive peeling machines use rotating material to strip the skin from each potato through mechanical friction alone. There are no blades. The action is firm but controlled. The water used in washing does not go to waste. It passes through a series of filtration and treatment systems before being recirculated. Sensors monitor the clarity of the water continuously. In slow motion, the force of industrial washing becomes visible. Each jet of water impacts the potato surface with considerable pressure, dislodging particles that a simple rinse would never remove. The first active stage of processing is washing. This is not a gentle rinse. High-pressure water jets and mechanical tumbling action work together to strip every trace of soil, debris, and field contamination. When a batch is cleared and production is ready, the potatoes begin their journey through the facility. From this moment forward, they will not stop moving until they emerge at the other end as a finished, packaged product. Approved batches are moved into controlled storage. Temperature is held within a narrow range, cool enough to slow any further conversion of starches or to trigger what it is trying to prevent. Every hour in this room is monitored. Nothing is left to chance. Sugar content is measured with equal precision. During frying, natural sugars in the potato react with heat and produce color. Too much sugar, and the chips darken too fast, becoming bitter, uneven, and visually inconsistent. Dry matter content is one of the most important values measured at intake. It tells the factory exactly how much solid, usable material is present relative total weight to total weight. Every number on this display is a decision point. Samples are taken from every incoming load. Laboratory technicians assess the physical condition each batch, each invisible batch, but the most critical measurements cannot be seen with the naked eye. They require instruments. Every delivery that arrives at this facility is treated not as a routine intake, but as the first quality control checkpoint. The truck does not simply unload and leave. What happens next determines whether this batch will ever become a finished product at all. From field to facility, the potatoes travel in bulk. At this point, they are raw, unprocessed, and completely ordinary looking. No one watching this truck pass would guess that these tubers are destined to become one of the world's most precisely engineered snack products. At harvest, the machine does the work that once required entire teams of people. As the harvester cuts through the earth, pale tubers emerge in steady streams. It starts in the soil. The potato variety selected for this process is not a standard potato, it is above all others. Low moisture content. Less water in the raw material means more control at every stage that follows. Before a single chip is made, the journey begins here, in open fields, where a very specific variety of potato is grown under carefully managed conditions. There's no accident.